Hi everyone, I'm the presenter Sunghye from Pohang University of Science and Technology. Today, I'll introduce our fast and scalable Qubit-Mapping method for those intermediate-scale quantum computers. This is outline. First is introduction. Next, I will present our proposed method. After that, I will present the experimental setup and result and summarize the presentation. First, I'll introduce why do we need an efficient Qubit mapping. Recently, quantum computing has attracted great attention, so the development of quantum hardware is rapidly progressing. To perform quantum computations, qubit is used as a basic unit, and it uses quantum phenomena instead of classical physics. The left figure shows that the number of qubits is increasing exponentially. Now, current quantum hardware reaches 50 to a few hundred qubits. However, the current quantum hardware is called the noisy intermediate-scale quantum devices. As the name implies, the current hardware has limited qubit resources and is prone to noise. Moreover, the schematic of the hardware shows the limited connectivity between qubits. In this work, we focus on the connectivity problem in executing quantum circuits. Then, how do we execute the quantum circuit on the current hardware? First, we map the logical qubit to the physical qubit. In this example, the logical qubit denoted by lowercase letters compose the quantum circuit, and the physical qubit denoted by uppercase letters compose the hardware. Then, the quantum hardware must operate the quantum logic gate in the circuit step by step. In here, CNOT gate, which is the general 2-qubit gate, can only be executed when the pair of logical qubit is connected onto the quantum hardware. So, these three gates can be executed in sequence. However, the gate with number 3 cannot be executed because the logical qubit Q1 and Q2 are not connected on the hardware. The same applies to the gate number 5. To solve this connectivity problem, we need a qubit mapping. Now, I will explain about qubit mapping. Qubit mapping is a procedure to modify the quantum circuit to satisfy the hardware constraint. To increase speed and scalability of qubit mapping, heuristic approaches are generally used, and it consists of 2 steps. The first step is to find an initial mapping. Initial mapping refers the connection between logical qubit and the physical qubit, and this stage determines the gate constraints. The next step is the main mapping. If the connectivity constraint is violated in certain gate, it solves the connectivity problem by adding gates. However, the additional gates used to solve the connectivity problem increase the depth of the final circuit. Since the NISQ devices can only maintain the state of the qubit for a limited time, this increased depth also increases the error probability of the final circuit. So, qubit mapping requires minimizing the number of additional gates. After scheduling all gates, we can execute the modified circuit on the NISQ devices with satisfying hardware constraints. Now, I'll present our qubit mapping method. In the qubit mapping problem, we are given the quantum circuit and target hardware as inputs. Then we modify the quantum circuit to satisfy the hardware topology with minimizing the number of additional CNOT gates. This paper proposes an efficient qubit mapping method for scalability and fast runtime. It consists of 3 steps. Step 1 is initial mapping. Step 2 is main mapping. And step 3 is post-optimization. The first step of the proposed mapping is an initial mapping. To minimize the gate overhead, the best mapping solution is an isomorphic graph between the quantum circuit and hardware. The reason is that every interaction in quantum gate can be connected on the hardware. Initial mapping with the graph isomorphism search consists of two steps. The first step is to represent the circuit as an interaction graph, and the next step is to match the interaction graph on the hardware. To find an isomorphic graph, previous method used only one center and then expand all nodes around the center. But our proposed method uses multiple centers to have higher scalability. Then we expand the child node in the subtree from each center. We iterate the center mapping and child node mapping until the graph matching is complete. On the next page, we describe the proposed method in detail. First step of our initial mapping is representing the circuit as graph structure. So we create two interaction graphs. In both graphs, each node represents logical qubit, and the H indicates that there is an interaction between two nodes. The H weight of the interaction weight graph corresponds to the number of CNOT gates in the circuit. And the interaction order graph uses the first appeared index of the CNOT gates. By using these two graphs, we determine our recursive graph matching order. To find the isomorphic graph, we iterate mapping of each logical center and each child node mapping. To determine the order of the center mapping, we use the interaction weight graph. In this way, we can consider the qubit in descending order of the number of CNOT connections. After mapping the center, we expand the child node in the subtree using the interaction order graph. In this way, we can maximize the possible interaction for each center. Then we iterate these two mapping. After all graph matching is completed, we use the result as the initial mapping solution. The next step of our method is main mapping. When we execute the gate sequentially with the generated initial mapping, we solve the connectivity problem by inserting the swap gate. In here, adding swap gates can exchange the state of two adjacent qubits. Then, these three gates can be executed with the updated logical to physical mapping. However, this updated mapping may affect the connectivity constraint of the rest of the circuit. Therefore, to minimize the additional gate count for the entire circuit, we propose an adaptive Rugoid window search. Now, I will explain how to select the swap gate among candidates. When executing the gate 2 in this example circuit, there is a connectivity violation because the physical distance between two qubits is 2. So, we must insert the swap gate in front of gate 2. To select the swap gate, we'll calculate the heuristic cost. We compute the difference of the distances between before and after swap, and if the computed result becomes +1, corresponding swap gate can solve the connectivity problem by reducing the physical distance. So the first swap gate is used. But computing the delta distance for only one gate is insufficient. So we also consider the last gate using the Rugoid window. For the Rugoid window, we apply an exponential discount factor. In this way, we give a more lever to solving the connection problem at the front gate. And we can reduce the size of the search space. To solve the connectivity problem, we also use the bridge gate. In the case of bridge, one CNAP gate with distance 2 is converted into 4 CNAP gates with nearest neighbors. So the bridge gate can solve connectivity problem without changing the logical to physical mapping. When selecting the gates between sub and bridge, we use our cost function. After all mapping processes are completed, we perform post-optimization to further improve the mapping quality. Since quantum gates are reversible, the Qubit-Mapping method can also be applied to reverse circuit. Then we get a new opportunity to update initial mapping. So we perform Qubit-Mapping multiple times and then return the final circuit with the best result. These are all processes of our proposed algorithm. Now I'll present about simulation setup and result. Our proposed algorithm is implemented in C++. For the evaluation, we use the Kazan file as benchmark circuit and IBM Q as target hardware. Then we compared both the number of additional CNAP gates and the compile time. When performing the post-optimization, we iterate 7 times like the previous method. We first compare the overall performance of our Qubit mapping. The two tables on the left describe the comparison result, and the figure on the right describes the normalized result to our method. For the benchmark 1, our method reduced the gate overhead and runtime by 39% and 95% respectively compared to several. For the benchmark 2, we reduced the gate overhead and runtime by 22% and 68% on average compared with the state-of-the-art MCPE. Therefore, we can effectively solve the connectivity constraint with the lowest gate overhead and runtime. We also evaluated the individual steps of the proposed algorithms. First, we evaluate our initial mapping. For fair comparisons, we only use the sub-gate and not perform post-optimization. As shown in the left figure, our method found the optimal result for very small circuit. Moreover, we returned the scalable solution for large circuit with a decrease of about 8%. Next, we evaluated our adaptive overhead window with using bridge gates. For the main mapping analysis, we use an identity mapping as the initial mapping. In this experiment, we did not perform a post-optimization. Then we reduced circuit overhead by 24% on average. In addition, we analyzed the scalability and stability of our method. To evaluate scalability, we plotted time complexity according to the gate size. When we plot the runtime of previous works, they have polynomial time complexity. But our Qubit mapping can achieve linear time complexity. Therefore, we prove that our method is highly scalable. As I mentioned earlier, due to the limited time of disk devices, the circuit depth determines the stability. So we perform the depth analysis to evaluate the circuit stability. As shown in the right figure, we can reduce the additional depth compared to the state-of-the-art. The reason is that we can compare the circuit with only a few additional gates. Now I conclude the presentation. In this work, we propose a fast and scalable Qubit mapping method that effectively solves the connectivity constraint. Our method achieves significantly better results than the state-of-the-art in terms of best gate overhead and runtime. In the future work, we plan to improve the Qubit mapping considering actual hardware constraints. This is the end of the presentation. Thank you for listening.